in the talk. Okay. Yeah, so welcome everyone to CTMP. I am pleased to introduce Professor Konstantinos Zoubos from University of Pretoria. Kostas completed his PhD studies at Stony Brook, New York in 2004. After postdoctoral appointments at Queen Mary, University of London, and the Niels Bohr Institute in Copenhagen, he joined the physics department at the University of Pretoria in 2013. His research focuses on several aspects of high-energy theoretical physics, such as the ADS-CFT correspondence, integrability in gauge theory, and mathematical structures, such as quantum groups. So now I hand over to Professor Zoubos. Looking forward to your talk.
All right, thanks, Frank, and thanks for the invitation to present my research in this series of seminars, which I think is a really great initiative. So I was asked to prepare two talks, one which would be kind of a little bit giving the background for what I plan to discuss next week, which is kind of my actual research, well, one of my main research topics at the moment. So I decided to make this talk a bit more like a Blackboard talk, just so that I don't go way too fast through everything. And then next week will be probably a more normal slides talk. Okay, one thing before I start is we do sometimes get load shedding here, and I'm on a laptop. I'm on a desktop. So if I suddenly disappear, then don't worry. I'll join in from my laptop a couple of minutes later. All right. So the main points I wanted to discuss in this presentation is first of all some quick discussion of the Heisenberg spin chain, which will be quite important in the next talk, or it's some of its more exotic cousins, I would say, are going to be quite important. Then I'll switch gears to talk about four-dimensional gauge theory, and in particular, I want to say a few words about the planar limit of four-dimensional gauge theory. Then I'll use that as a starting point to say a few things about the n=4 Superyang-Mills theory and one of its important properties, which is superconformal invariance. And then finally, I'll go full circle and go back to integrability through the dilatation operator of the n=4 theory. Right, so at any point, of course, you're welcome to stop me if something is not clear, or if you feel that, okay, maybe it's too clear, or maybe I'm taking too long on something simple, I'll be happy to also skip some of these things. All right, so let's start with the Heisenberg spin chain, which was proposed in 1931 by Heisenberg as a model of a ferromagnet. So the way this chain is constructed, it's a one-dimensional quantum mechanical system. And the idea is just to take a line, a one-dimensional lattice, and put at the lattice points some spins. Okay, so you have lattice points labeled by L. So you have 1, 2, up to L, up to big L. And then you all of these have, at least in the original version, spin half, which means that there are basically two possibilities if you take the usual basis that we take for spin half. So either at site L, the wave function will be pointing up or down, the spin projection will be pointing up or down. And you can also consider, okay, now you need to describe what this Hamiltonian acting on this spin chain is. So for that, we need our spin operators, the usual spin operators. I'm not going to put the H bars here, but otherwise this is the same as in your quantum mechanics, with the usual Pauli matrices as our fields and sigma z. Right, so this is a very, at least to describe it or to define it, it's a very simple system. So we have this Hilbert space composed of the product of all these Hilbert spaces of spin half spins at each site. And then we want to act on this with a Hamiltonian, which, okay, with some not so important overall normalization, is going to be given by a sum from 1 to L of this operator here, which is the product of the spins, which you can also write as sum L=1 to L, 1 minus sigma L in the the X Pauli matrix, the Y one, and the Z one. Okay, so what you can see here is that this interaction that I'm giving, so this, well, of course, acting on a given spin or a spin configuration is going to alter that spin configuration because of the properties of the Pauli matrices. You can see, though, that it's nearest neighbor, right? So its spins are just next to each other. And I'm instructed to apply this operation from L equals 1 up to L with usually some periodic boundary condition, which is that, let's say, S sigma, or for all the sigma L plus 1 is sigma L, or sigma 1, sorry. So that's, impose some periodicity here. So you can think of this as living not really on a line, but on a circle where L plus 1 is identified with 1. Okay. One important aspect of this chain, which we're going to see appearing in a second, but you can also just directly prove it, is that it's SU2 symmetric. Meaning that it commutes basically. So the Hamiltonian commutes with SU2. So you kind of expect that representations of SU2 are also going to have anything that belongs to a multiplet of SU2 is going to have the same energy since the Hamiltonian and SU2 commute. We can immediately see it if we, for instance, act on two sides. So let's act on two sides just for simplicity. So the Hamiltonian, if you write it out for two sides, then it's going to look like 0, 4, minus 4, minus 4, 4, and 0 in the basis where, for the two sides, both of the spins are pointing up. One is pointing up, the other down, down, up, and down, down. Okay, so that's my basis. I'm working with two sides, so I have only 4 possibilities. And what we can see is that, again, this is not, I'm not going to go through it now, but it's not so difficult to diagonalize this, because obviously, as you know, the up-down is not an eigenstate of spin, and neither is, of course, an eigenstate of the Hamiltonian, but you can easily diagonalize it and get the triplet. And it turns out that the triplet with this Hamiltonian has an energy of 0, while the singlet has an energy of, I believe, 8 in the units that I'm using here. Now, the reason this spin chain is ferromagnetic is because it has, obviously, we call it ferromagnetic because it has a vacuum, and which is, let's say, the state where all of them are pointing upwards. So this is true here. You see that this state, which is part of the triplet, has energy 0, and its whole multiplet, of course, has energy 0. But all that extends to any number of sides. The states which have all the spins aligned, either all pointing up or all pointing down, or of course anything in that multiplet that you would get, have energy 0. Right? Yes.
Is this matrix here not going? The Hamiltonian should it not be like 2L times 2L? So you can have like block diagonals of the Hamiltonian you wrote down there.
Is the question if it should be 2L times? You mean? Well, it's so this Hamiltonian, yeah, okay. So here I'm just acting on on two sides, right? So there should be 4. I guess here I'm really acting, sorry, on I'm not doing the closed version. So I'm just acting on an open chain. Of course, if you close it, so basically on the two sides, I'm only acting on. Let's move this a little bit. I'm only acting on these two sides. I'm not doing the action on these two, which should also be there for the periodic case. So if I did that, then I would get more terms here. But the Hamiltonian should be 2 to the L times 2 to the L in general, and here L is 2, so it's 4 by 4. Okay, so obviously these are. Is that answering the question? I'm not sure.
Yeah, thank you.
All right, great. Okay, so another way of writing this Hamiltonian, which is kind of useful, is to write it as 4 times the identity matrix minus the permutation matrix, where the identity on this, let's say, 2-side Hilbert space, but this generalizes, is just the 4x4 identity matrix, and the permutation is this matrix here. Everything else. Okay, so when I don't put things, it's just 0. And it's something like this, which permutes 2 sides. So if it had up, down, it would give me down, up. And as you can see from acting on this basis. And so if, for instance, you can write the Hamiltonian on up, down, as I just said, as giving you 4 times up, down, but then minus 4 times down, up. So it mixes these states. The up, down, of course, is not an eigenstate, as we said. It also contains a bit of down. No, so much, okay, so far everything is kind of trivial, and you can easily diagonalize this matrix. And if I gave you 3 sides, you could also easily diagonalize 3 sides or perhaps 4 sides. But our goal, or at least the goal that kind of started out the subject of integrability for the spin chains, is you want to go to L sides, where L could be large, and L could in principle be in the thermodynamic limit. So L could be 10 to the 23. So how do you diagonalize such a spin chain if you have 2 to the L times 2 to the L, but with L large? That very quickly becomes a very difficult problem, even on a computer. So the idea is to kind of try to use alternative techniques to do this diagonalization rather than relying on just brute force. And for that, one notices that since the Hamiltonian, as I mentioned, commutes with spin, it also commutes with Z, the Z component of the spin. So you can divide the problem into Magnon sectors. And what I mean by that is that you can write this state, which is a vacuum, everything is pointing up. And by acting with a Hamiltonian, you're never going to get a state which has 1 down. Right, so this is 0 magnons, you would call it. This is 1 magnon. And again, if you had 2 down magnons, then that's a 2 magnon sector. So all these sectors are independent from each other under the action of the Hamiltonian. They don't get mixed. So it's worth considering each of these sectors independently. And for the 0 magnon sector, there's not much to say. This has energy 0. There's only a single state. Here you have L's possible states, because this site can be site L. And here each of these magnons can be at some site, L1 and L2, and so on. You can continue to more magnons. So what Hans Bethe kind of studied this chain in around 1932, did for the 1 magnon sector, so this is about 1932, he looked at the 1 magnon sector and said, okay, how do you diagonalize this? You write a state which is a linear combination of all your spins. So L is the state of so either up or down at site L, that's my convention for this. And then he just puts an e to the IPL in front, as if this is just a plane wave. That's the ansatz. So that's called the Bethe ansatz for 1 magnon. Sorry, for 1 magnon. And then you can take this, plug it into the act with the Hamiltonian, and see how. I'm not going to do this calculation, but you can act with the Hamiltonian on this state, and you want to find the eigenstates. So you want states that have a different energy. And what you find is that this is an eigenstate, but the energy has to be quite specific. It has to be 8 times sine squared of p over 2. So there's a dispersion relation that you get by acting on a single magnon. Okay. Now we want to proceed to 2 magnons. And knowing about the 1 magnon, then we go to 2 magnons, and you do the same. So you write psi to be a sum. Now you have 2 L's, because you have 2 magnons, and they can be different positions. And you can think of some function of the momentum of the magnons times e to the I p1 L1 plus I p2 L2 times the states of those two magnons. Now, what I mean by the state is that, here everything is pointing up. So when I write L1, I mean there's the state where everything is up, apart from this state which is pointing down. That's what L1, L or L meant here. Here, I mean the same, that it's a state where everything is up, apart from those two. And now take this, plug it into again the Hamiltonian, try to diagonalize, and you find that you cannot do this. So this does not give you an eigenfunction, the Hamiltonian, unless you add another term. So here you need to add one more term, which is the sum of another wave function, but now where you have the momenta interchanged. Okay, and times the same L1, L2. So you need to add this extra term where the momenta are swapped. And if you do that, then you can find the solution. And I'm not going to write again the solution, but it's not so difficult to act to the Hamiltonian and see that these terms need to talk to each other for you to get a solution. And you can phrase that solution in terms of an S matrix, which, just to give you a flavor of how it looks for those who haven't seen it, is basically the ratio of this B over A, which is minus 1 minus 2 e to the I p1 plus e to the I p1 plus p2, and minus 2 e to the I p2 plus e to the I p1 plus p2. So you can, if your S matrix, if the ratio of these functions is precisely this number, then you can diagonalize this and you can solve for the energies, for the two-magnon system, and so on. All right, so this was kind of straightforward, and this you can more or less always do for a two-magnon system, for any more or less Hamiltonian that you are given. It's called the coordinate Bethe-ansatz. However, you want to go further and you want to look at M magnons, because you want to solve the full spin chain. And it turns out that for more than two magnons, you hit a problem, and this is only possible to do if this S matrix satisfies a specific condition, which is that if I were to draw this, and I were to draw this, I'll explain what I mean. So here you have 1, 2, and 3. So the way you are thinking about this, and the way that Bethe was thinking about this problem, is that if you have your spin chain here, and you have your two magnons, the ones that are pointing down, and they're moving with some momentum, P1 and P2, then what happened is this term describes the situation before they scatter, and this B describes the situation after the scatter, so when P2 has gone through P1. And you can generalize this to have more magnons. That's why this is called the S matrix, because it has to do with the scattering of the two magnons. You can try to generalize this, but you only get an answer if your magnon scattering satisfies this equation, or you're able to get a decolonization if you satisfy this equation. So this means that here 1 and 2 scatter first, then 1 and 3 scatter here, and then 2 and 3 scatter, and that is equal to when as 2 and 3 scatter first on this side, then 1 and 3, and then 1 and 2. And this relation, much later, was called the Yang-Baxter equation. Okay, so basically what it tells you is that when you have a 3-magnon scattering, there is some kind of associativity in the game. So you can choose to first scatter the first two and then the third one, or the second two and then the first one. So it is very strongly related to associativity of the scattering problem, and that is very strongly related to integrability. So without this condition, you don't have integrability. You cannot break down your 3 magnon scattering into a 2 magnon scattering, and then basically you. I mean, I'm not saying you can give up. There's other approximate methods to solve the problem, but definitely you cannot apply these integrable methods. So this so far was, okay, that's all I'm going to say today really about integrability. We're going to come back to this in the next talk, but I just wanted to give you some of the main features that will appear in the next talk, in particular also for a given spin chain, how you would start thinking to diagonalize a given problem. Are there any questions before I move on to the next part of the talk?
Yeah, perhaps one that's kind of obvious. We want to go to L magnon segments eventually.
Yes.
So is the associativity relation does that exist for just any number of magnons? You have to have this associative property.
Yes, so exactly. So this allows you to, when you have it for 3, then you can break down the problem for 4 magnons into the one for 3 magnons, and then into that for 2 magnons. So you can keep breaking down the problem into smaller parts, and then associativity hits at any number of magnons basically. So then you get a unique answer. Of course, if you have more magnons, then you have many more terms in your answers, because let's say for 3 magnons, you still need 6 terms, but that because you have 6 combinations, but they can all be written in terms of the same type of S matrix.
Yeah.
So every time you scatter, because you see the problem of multiple magnons, if you look at the picture, even if you had more magnons, you can always say, well, first these 2 scatter, or first these 2 scatter, then this one with that one, then that one with that one. So every time you apply the Yang-Baxter equation to kind of see that the scattering is associative at that, for those 3, for that region, where there are 3 magnons contained, and then you can continue with the next magnon.
Okay, thank you.
I also have a question, Kostas, if you can hear me.
Yes.
This relation, the relation for 2 magnons, the one that you have written at the top of your slide, that looked pretty much like the consistency condition for the Hirota method. Is there any link between Yang-Baxter and Hirota, Yang-Baxter and tau functions?
Yes, yes, of course. Tau functions were developed, as one way of describing. Okay, that of course is for classical integrable systems, right?
Yeah.
So you are using tau functions, this determinant, whatever of Hirota, in order to be able to write down, let's say, multi-soliton solutions for a classical system. But underlying that, unless I'm very much mistaken, is like some transfer matrix or some monodromy matrix, right? That is being rewritten in terms of the Hirota equation. And if you think of the transfer matrix, the condition for that, which effectively is some kind of flat connection and all that, can be phrased in terms of a classical Yang-Baxter equation. So of course, here I'm doing quantum integrability. There's also a classical version of this, where you can expand each of these matrices into, ideally would write an R matrix, which is the identity, or 1, 2, plus some, maybe there's an H bar here, and you have some classical integrability, and then using these techniques of Lax pairs that satisfy some classical Yang-Baxter equation, you can, I think, effectively get to the Hirota formalism. So I think it's all very much connected. Although definitely, I mean, here I'm really just doing spin chains, and I'm not I don't have a quantum tau function to write down for you, because that's more for the classical case.
And what will be the classical analog for the Heisenberg spin chain here?
Well, to get something classical here, I think what you need to do is take a kind of long wavelength limit.
So what are you going
because you want to make it, of course, a continuum model, right? So this is a lattice model, because things live on a specific. But you can take a long wavelength limit, basically taking your lattice constant to be very small compared to the wavelength of some excitation, and you will get something, something quite quite simple. Perhaps for this case, we'll just get some. Is it sine Gordon? Maybe I'm a little bit unsure.
Could it be Landau-Lifshitz equation, something
Yeah,
like that?
yeah. So yeah, you're going to get some Landau-Lifshitz, of course. Some in this case non-relativistic. Yeah, you're right. So it should not be non-relativistic in this case. It would be some kind of Landau-Lifshitz type of equation, which you can analyze using techniques of classical integrability. This is very important in many aspects of ADS-CFT that I'm going to come to now in a few minutes. But I won't need it in this talk. The link to long wavelength and to Landau-Lifshitz, although it's something that a student and I are working on for what I will discuss next week. So I might come back to that if I'm asked.
Right, thank you.
All right, so let's now move on to something totally different, which is four-dimensional gauge theory. Because, okay, I mean, you could say that spin chains are interesting per se, but let's say, where I'm coming from, the direction I'm coming from is more, we want to understand four-dimensional gauge theory. And we want to understand in particular, of course, as many people, I think, in the room, QCD. And QCD is a theory based on a gauge field, A mu, AB. AB are the gauge indices, which, of course, it's a field. It lives, it's a field depending on X, and it's an SU3 gauge field, which means that these indices go from 1 to 3. So you get, it's a 3x3 matrix, but traceless because of SU3, plus quarks. Okay, which also have a gauge index, but they're in the fundamental. So SU3, you think of the AMUs as your gluons. Normally, we would write them as R bar, R green bar. This is just more for the students. G A bar. And BB bar with a traceless condition. Okay, so that's your gluon, and the quarks would just be in the fundamental, meaning that you have 3 quarks like this. Okay, so this is in the adjoint representation. That's going to be important. All right, so now QCD, of course, is very important because it describes a strong interaction, the strong interactions, but it has, of course, many complications, in particular that there is a running of the coupling, of the gauge coupling. Which means that the interactions become strong, well, because the beta function, which I'm going to write maybe a few slides later, but it becomes strong at low energies because the beta function is negative, and that's precisely the regime where we want to understand bound states of QCD, like mesons and protons, but perturbation theory is not very effective in that regime of low energy. So one of the techniques that people came up with to understand how to do QCD kind of beyond just perturbation theory is came up with the work of 't Hooft around 1973, where he proposed to take this SU3 and go to SUN with n large. Okay, in principle, going to infinity. And when you do this, so you take the rank of your gauge group to be large, but you keep a combination of your gauge coupling and the rank of the gauge group fixed. And when I say fixed here, it can be fixed to be a small value, or it can be fixed to be a large value. So this could also kind of tend to infinity. So it's not so important that the value of this be very small for what I'm going to say. But definitely, if you want to do perturbation theory, lambda should be, this combination should be fixed to a small value. Okay, so to see why this is relevant and what this kind of helps with, let's think, for instance, of double line notation, which is also something that was important for 't Hooft's treatment. So normally we have a gluon, So if you want to write your gluon, a mu, a b of x, and a nu of c, d of y. So normally I would write this as just something like this, to the propagator with a particular choice of indices, but you can also be a little bit more explicit with the indices and write it as delta AD, delta CB minus delta 1 over n, delta AB, delta CD, times your usual propagator, which I'm not going to need. So this is the propagator for a single photon, and this is the part because of the non-abelian structure of SUN. And you can imagine this as connecting the indices in this direction. So the upper indices go like here, and the lower indices, sorry, this goes, it's upper from here, but lower from this direction. And then this is the B, the lower index, which connects to C, minus 1 over n, this way of connecting your indices. So A and B go back to themselves, and D and C go back to themselves. So the propagator can be written in this way. And you can, so instead of just writing down the gluon, we're going to be using this double line notation where I'm kind of showing the flow of the indices from A to D and from C to B in this particular way. But of course, the top index goes in this direction, the bottom index, you put an arrow in the opposite direction. And you can already see one simplification if you take n to be large, which is that this part kind of falls away. So you don't have to worry about these combinations in general. But there's an even bigger simplification, which is that, okay, let's say I write my Lagrangian of my theory with the gauge coupling in front. And this would be the usual Lagrangian, a trace of f mu nu, f mu nu. Plus you could consider other fields, but let's be focused only on the gauge field. Then what you get is if you rescale things to talk about the 't Hooft coupling, so this is called the 't Hooft coupling, is that your vertices of your theory now all go as n over lambda. You can kind of see it because n over lambda is just 1 over GML squared. Then all your propagators go like lambda over n. And there's one important ingredient that all index loops, so in this notation, if you have a loop of an index, that adds a factor of n. Okay, because basically there are n fields, n indices running in the loop, and that gives you a contribution of a factor of n. And if we do like a couple of maybe just quick calculations, let's consider, for instance, this diagram here. I'm going to write a diagram which is a for-loop diagram. Okay, sorry, my skills are not. Okay, so you have something like this, which has 5 vertices. So there's 5 vertices, 1 in this double line notation, 3, 4, 5. So then you would write n over lambda to the 5. Let's count propagators, 1, 2, 3, 4, 5, 6, 7, 8 propagators. That's lambda to the n to the 8. And then there are how many index loops? You can see that there are 5 different index loops. So 1, 2, 3, 4, and then the external index loop there. So this gives you a contribution of n to the 5, which together gives you a lambda cubed n squared. Now let's compare this to another diagram. I'm just kind of not writing anything in a particular region that I'm writing these diagrams, just to give some idea. So, of course, for a Feynman diagram, the given Feynman diagram in Yang-Mills theory, you can also definitely write something like this, where here there is no vertex. The propagators are just going on top of each other. So there's 2 propagators going above each other. And here you have, in this case, 4 vertices. 1, 2, 3. There's no vertex in the middle, so it's 4 vertices. you have 6 propagators, not 8. But if you count your index loops, there is one, the external one, and here all of these are a single loop. You can see that this goes like this, goes like this. You can write them as a single index loop. So in total, you only have an n squared from the index loops, which gives you a lambda squared times an n to the 0. Yes.
Do you see the origins of bird track notation that was exploited very, very widely elsewhere?
Do you see the origin of, sorry?
Of bird track notation, right? You know Sputanovic's
oh, yes, of course, the bird tracks, yes.
Yeah.
Yeah, but of course, here I'm saying something very simple, I mean, much, very simple, which is that basically the power of n for any diagram that you would write in double line notation goes like n to the chi, where chi is the Euler sort of number associated to this, which is the number of vertices minus the number of edges plus the number of faces for a given diagram. These are, of course, just 0-point diagrams. I mean, there's kind of, but you can do this. You can get the same for 1-point, 2-point, 3-point diagrams. You get some similar kind of numbers. And all that's important for me is that this one is subleading, right, at large n, which basically means that you can ignore it at large n, and the only ones which become leading for 0-point, 1-point, and so on, the only ones which are leading are the planar diagrams, meaning that they can be written on a plane. This is, of course, a non-planar diagram, because you cannot really write it on a plane. You need to write it on, let's say, a torus or some so this can be written on a sphere, basically. These can be written on a torus, and you can have other diagrams that can be written on higher genus Riemann surfaces. So the idea of 't Hooft and many other people, including Witten back in the 70s, was to just focus on the planar limit and then treat these as corrections, as 1/n corrections. And kind of the kind of logic is that, well, the mistake you're making by looking only at the planar ones is roughly 1/n squared. For QCD, you want 1/3 squared, so which is basically 0.1. So you're within 10% of the right answer if you are only doing the planar limit. So even though n is infinity looks like a not very physical kind of approximation, it's not really too bad. And actually, if you put extra factors of pi that should be there, this becomes a little bit smaller also. So that was the idea, like solve large n first, and then start worrying about the non-planar diagrams, which will give you the corrections. This was phrased back in the days in terms of something known as a master field, which would be a very complicated but kind of classical configuration that describes the physics of Yang-Mills theory at large n, which then you would kind of quantize away from that classical configuration with your quantum or your Planck's constant not being G Yang-Mills, but being 1/n squared. So you'll be quantizing the theory with 1/n squared being your Planck direction. And okay, there were many works back in the days about trying to understand this master field. It's kind of very complicated. But what kind of happened back in 97 with the introduction of ADS-CFT was that in many ways, people understood what this master field is in the large n limit of not of standard Yang-Mills or of QCD, but of another theory, which I'm going to come to the next slide and describe it. And that master field for this theory ended up being classical string theory. On a given gravitational background, ADS 5 times S5. So it's a 10-dimensional background. But you're doing on this background classical string theory, meaning just to what I mean by classical string theory is a theory of 2-dimensional surfaces, and classical string theory is where you only keep the ones that have a sphere topology. So there's a quantum expansion in string theory with a G string coupling constant, and this is identified in this logic with 1/n squared. 1/n to the 4, and so on. Okay, so that was somehow a big breakthrough in understanding the physics of gauge theory in the planar limit. But of course, it does not really work directly for QCD. So to get there, we had to make quite some significant approximations or kind of simplifications, because as I said, I mean, QCD by itself is a very difficult theory, but if you kind of make the theory a bit more symmetric, then you can start making some progress. So now I'll just move on to describe quickly this theory that I'm talking about, where it is possible to make very significant progress because it has much more symmetry. So are there any questions before I move on to n = 4?
I just want to check the number of faces and edges. Faces being, are those the number of index loops, while edges are propagators?
Yeah, I think faces. So you need to include the outside as a face as well, because you're thinking of this as written down on a sphere, essentially. So yeah, but that's the idea, that F is the number of index loops, and V is the number of vertices, like 5 in this case, E is the number of edges, meaning propagators.
Thank you.
So that's a formula, of course, that appears in many other settings as well, triangulations and all sorts of. All right, so I tried in these couple of slides just indicate why it's not so crazy to look at this planar limit. So I'll take that as given from now on, that we are interested in the planar limit, and we will be working with a theory that okay, some of you might find familiar, some of you might find a little bit too simplistic or too special, but I'll try to convince you it has very beautiful properties. So I'll take my group to be SUN. Okay, not yet in the planar limit, but we'll get there. And on this SUN gauge theory, you just add 6 scalar fields plus a corresponding amount of fermions to make it supersymmetric. I'm not really going to need supersymmetry here, so I'm not going to really introduce it in any detail, but it's just a symmetry between bosonic fields, like the gauge fields on the scalars, and fermionic fields. And you need the suitable amount of fermions in order for this thing to be supersymmetric. All of these fields are in the adjoint, okay, which is a big difference compared to QCD, where, as you remember, we had the quarks here, which are in the fundamental representation. Here, everything is going to be adjoint, so everything is n by n matrices. So no quarks in this theory. And also, they're all massless. Okay, so nobody has a mass. So these 6 scalars, which you can call phi I, you can also combine them. It's useful to combine them, and this is more for next week, where I'm going to need them, into 3 complex combinations. Right, and again, these are all n by n. And and now you need to talk about the interactions in this theory. How do these fields interact? Okay, of course, SUN gauge theory means you have the usual non-abelian, like Yang-Mills action for the gauge fields, and the kinetic terms for the scalar fields are the usual one with covariant derivatives. But there's also like a potential which makes these fields interact with each other, and for that it's useful to define the notion of a superpotential, which looks like this. It's a trace of X commutator YZ, so these fields, from which you can derive the actual potential as something proportional to X bar plus the same thing with a Y. This means Hermitian conjugation here, because of course you have the conjugates of these fields. dy bar plus the same with the Z bar. And this, as you can see, this is cubic. If you take one derivative, it becomes quadratic. And then if you combine it with its conjugate, you get quartic. So, the terms in here, they're going to look like YZ times Y bar Z bar plus other terms, but they're all quadratic. And there's something nice, of course, about quadratic scalar potentials, which is that the canonical dimension of a scalar in 4 dimensions is 1. So these are marginal terms in the Lagrangian. They have a dimension of 4. You can go a little bit further than just this for the specific case and show that this theory is actually perturbatively finite. And what that means is that any loop diagram that you would ever want to write down in terms of the fundamental fields of the theory, so take some phi, some scalar, could be any of these, and do some correction to the propagator, or do some vertex correction. This is one loop, but you could also go further. All of these are automatically finite because of cancellations between the bosonic fields and the fermionic fields. And maybe just for those who are familiar with QCD, you know what the beta function ends up looking like in QCD. It's something like minus g cubed over 4 pi squared. There's an 11/3 of the quadratic Casimir of the gauge group minus something like this, where this is the number of fermions. And this is what appears on the right-hand side of the trace of your algebra generators, C of R delta AB, right? So this, of course, is negative unless the number of fermions is large enough to kind of cancel this, and you get what we would call a conformal window, where your beta function can be 0. However, in QCD, that's never really true in all generality, because if you go to higher loops, then that will get broken. However, here, it turns out that because of the high amount of symmetry, if you manage to cancel the beta function at one loop, then it will keep being 0 at all higher loops. All anomalous dimensions are going to be 0 at higher loops, and so on. And maybe just to write the condition for finiteness is something, it looks a little bit different. Here it's something like this, where here I've included the fermions in what we call superfields, and here I'm looking at a vector multiplet, and this is just the usual. Sorry, this is not G, this is C. The Casimir, which is proportional to n for SUN. And this coefficient here, C of n, is also n for SUN, and because they're in the adjoint. So if you have 3 scalars, then that means you're summing from 1 to 3, and you get an equality here. And these are not just scalars, they have to have the corresponding fermions for this formula to work. So people noticed these formulas back in the late 70s, early 80s, and they studied these theories in quite some detail. Also, first perturbatively, of course, by just brute force calculation, but then eventually they came up with non-renormalization theorems, which I won't really describe, but were quite powerful in being able to go beyond just perturbation theory arguments and show that this theory is actually finite to all orders in the coupling. Okay, and what's the consequence of that, of having a finite theory? Of course, you have, that means you have scale invariance, but on top of that, you have, turns out that the scale invariance you have, because your beta function does not run, induces also conformal invariance. which is a much stronger and more powerful statement, which basically means that you have full invariance under a much bigger extension of the Poincare group than you might naively have thought. So let's look a little bit at the symmetries of this theory. So first of all, okay, we have these 6 scalars, phi1 to phi6, and they are, the theory is invariant under rotations of these 6 scalars. So there's an SO6 here, which rotates these scalars, and that's equivalent to an SU4. And to see that this equivalence, you have to, instead of writing the 6 scalars like this, you have to write as a vector, you have to think of writing them as an antisymmetric tensor with A and B going from 1 to 4. So this shows you that this is the antisymmetric 6 of an SU4 group. That's an internal symmetry, which just is the flavors of the scalars getting rotated with each other. We call it, it's called in supersymmetric theories an R symmetry. But perhaps more importantly, as I indicated, your Poincare symmetry, which is your usual Lorentz algebra times the translations, gets extended to what we call conformal, and actually in the end it will be superconformal. But first of all, you get the conformal group, which is SO2, 4, and that's equivalent to SU2, 2. So this is a generalized orthogonal group, and it turns out it's convenient. It's somehow an indefinite version of SU4, so you can write it SU2, 2. So that's what this means, SU4, but with some signs changed. How does it look for those who haven't seen the conformal group, or maybe let me write the full superconformal group? Generators. Okay, so let's count a little bit. SU4, as you know, is something which will have n squared minus 1 generators, so it's 15-dimensional, the same with SU2, 2. So we expect in this theory to have 15 plus 15, because we have these independent symmetries here. So we expect to have 30 bosonic generators, but also there are going to be some fermionic generators. If you write them all down, what you will get is the usual translations, the usual Lorentz rotations, which include the boosts. You're going to get a new kind of bosonic generator coming from the conformal algebra called conformal boosts. You're going to get an operator D called the dilatation operator. And you're going to get, as bosonic generators also, 15 generators which come from these rotations here. So these RAB that I wrote are the R symmetry generators linked to this SU4. These generators are linked to the SU2, 2 here. Plus, these are the bosonic ones, and then the fermionic ones are called Q alpha A and S alpha A. These are the usual supersymmetries, and they're the conformal supersymmetry generators, and A goes from 1 to 4 because it's n equals 4 theory. That's what n equals 4 really means. You have 4 Qs, but now if you count generators, this index is a fermion index. It's a Weyl fermion in 4 dimensions, goes from 1 to 2. And these are 4, so you get 8, but you can also have their conjugates, because this is a parity invariant theory, so their conjugates are also there. So you get 16 generators. So 2 times 4 is 8, but then the conjugate is 16 plus 16. That's 32 fermionic generators. Here, if we count, you have the 4 translations, the 6 boosts, 4 conformal boosts. These are 15. This is 1, the dilatation. So together you get 30 bosonic generators. And all of these together give you the structure known as PSU2, 2/4. So this is a supergroup because it includes also the fermionic generators. I'm not going to really discuss the structure very much, but that's exactly what it implies. The P is a projective version of SU2, 2/4, meaning that you've removed one generator, that extra generator that would have been there. But that's, it turns out, the correct way of getting this. Yes. Hello?
No, no question, I think.
Oh, okay.
It was just
Good.
noise.
So, sorry?
It was just noise in the background.
Oh, okay. Great. Okay, so the focus here, okay, so there's a lot to say about the superconformal group, and there isn't too much time to really go into this in detail, but I want to emphasize one of these generators, which is going to play the biggest role in the next slide and in much of the rest of the next talk as well, which is this one. This is known as the dilatation operator. Okay, so it's something that only appears in conformal theories because it's part of the conformal algebra, and in this case also the superconformal algebra. For instance, it appears on the right-hand side of the commutator of these, the translations. So normally translations, of course, commute with each other, but here you also have these conformal boosts, and if you compute them, you get the dilatation operator appearing on the right-hand side, plus Lorentz boosts. Now, of course, the structure of the superconformal group is quite complicated, so I'm not going to go through everything, but just to show you that it appears here, but also in many other places. So if you take these S's and the Q's, the fermionic generators, also here, you'll get on the right-hand side, there will be more terms, but there'll be a term which also contains this D. So it is one of the generators that appear. And the reason that it's so important is that, and maybe it deserves its own slide. So let me just say the dilatation operator. And maybe let's add integrability here. Okay, so this is going to be the last part of this talk, so I'm kind of close to the end. Maybe I still need 10 minutes if that's okay. So now by going to this, we haven't been to the planar limit yet. I'm just talking about n equals 4 for any n here, for any SUN. But in any conformal theory, the operators of the theory and the fields, and the fundamental fields, but in general, any operator, are eigenfunctions of D, of the dilatation operator. So for instance, let's consider some gauge invariant operator. Because it's a gauge theory, so anything we write, if we want it to be a physical operator, it better be gauge invariant. How do you make things gauge invariant? You take a trace, everything is matrices, so you need to have a trace of, say, our fundamental fields. You could also add more things. You could add some fermions, which I haven't really discussed, and I'm not going to need. You could also have covariant derivatives of some fields, and so on. So anything you can build up from your fundamental fields. Of course, if you put a covariant derivative, then I better put maybe an index here as well. So these kinds of operators, which are gauge invariant, have to satisfy that D of O of X is, okay, some constant times delta times O of X, where delta is known as a dimension. Okay, so it basically tells you that because you have superconformal symmetry, you're allowed to rescale your theory. You can change your scale, and all your operators should give you back the same times a number delta, which is called the dimension of the operator. So this is going to be our main observable for superconformal theories, or for conformal theories. So it doesn't make sense to talk about the mass. You know, in QCD, we talk about the mass of the proton, but of course, here everything is massless and conformal invariance is preserved, so you cannot have masses in theories like these. But what you have instead is dimensions for your operators. And imposing superconformal invariance, or even just conformal, imposes very strong constraints on correlation functions. Okay, so for instance, you can look at a two-point function of an operator and a conjugate operator, and this will be some constant over x minus y to the 2 delta, but only if these operators have the same dimension. If the dimensions are different, if delta 1 is not equal to delta 2, then you just get 0. So that's an important constraint that you can prove using the conformal group. And similarly, you can prove constraints for 3-point functions, or 1 or 2. Okay, so that looks like some coefficient here, but what's important is the structure. You get something x minus y delta 1 plus delta 2 minus delta 3, x minus z of delta 1 plus delta 3 minus delta 2, and then a y minus z. So, and again, they have to agree. So the sum of the dimensions has to be 0. Otherwise, you will get 0 here. And if you want to know more, okay, conformal invariance kind of stops here. It doesn't constrain the 4-point functions. You can still get, different structures on these ones, but then you can use another property of conformal field theory, which is the OBE expansion, which tells you that two operators that you take close to each other can be written as a sum of single operators. So 1, 2, and k of some OK at that point x. So applying the OBE to correlation functions actually in principle says that you can solve, you can find any correlation function in a conformal field theory as long as you know the 2-point functions, where the only thing that you don't know in principle is the dimension here, and as long as you know the 3-point functions. Then in principle, of course, this is the start of a much bigger discussion regarding the bootstrap and how you can use this OBE to bootstrap higher point functions from lower point functions. I'm not going to get there, but you can in principle solve the whole theory. So if you give me a theory where you know all the deltas, so all the dimensions of all the fields and all the correlation functions, then you can solve the theory. That's what we mean by solve a 4-dimensional theory. Right. So of course, this is not an easy problem, and even though n equals 4 is conformal, then you and even though it has a dual, a gravity dual, still all this information is not really enough to be able to do this in practice. However, there's a last element, right, of the theory, and that's where we're going to go back to the beginning and get back to integrability. So what are we trying to do? We would like to solve, as a first step, the spectral problem. Meaning finding all the deltas. Then as a next step, we would like, so this would give us all the 2-point functions, because if you know the deltas, well, if you know all the operators in the theory with their corresponding dimensions, then you know all the 2-point functions. Then you can plug that into the 3-point functions and try to get all the 3-point functions. And then if you know that, then you can go further. So we would like to solve the spectral problem plus all the correlation functions. And if you can do that, then you can claim to have solved a non-trivial interacting 4-dimensional field theory, Gates theory. However, this runs into the problem that there's a very huge mixing problem. Because, well, what's a typical invariant operator? Let's even focus on a simple, what I call SU2 sector. So I can write my O of x. What I mean by SU2 is that I consider only operators which are made up of 2 fields, we'll call them x and y. My Gates invariant operator is going to be something with some x's, some y's. Okay, and in principle, any length can enter here. And you want to ask, what's the dimension of this? Classically, there's not much to ask. So if you write the dimension, there's a classical dimension. So before you quantize the theory. And here, all your scalars have their classical dimension of 1. Right, so this is just L. If you have L scalars, then this is the classical dimension, just L. And now we want to know what is the 1 loop anomalous dimension, right? That enters here, because of course this will depend on the coupling. There will be a G squared somewhere here. In order to do this, of course, you need to, in principle, at least it's kind of simple. You just take D. And you want to diagonalize this operator. knowing how the dilatation operator acts on fields. But of course, this is not going to be an eigenstate of your dilatation operator by itself, because you need to, that's what I mean by mixing problem, you need to diagonalize. So this operator is going to give you the same operator, perhaps with some coefficient. So this is called this O1, going to get O1 plus many more operators, O2 plus O3, right? Because that's how the dilatation operator acts. It doesn't just naively act on, it doesn't naively give you an eigenstate. So this is where a major breakthrough happened with the work of Minahan and Zarembo in around 2002, where they realized that, let's focus on these operators. And what you want to solve, as I just said, is the one loop anomalous dimension. So you want to find the one loop dilatation operator. And again, the classical dilatation operator is very trivial. I mean, it just gives you an eigenvalue of 1 for each scalar, just a classical dimension. Now you want to calculate the one loop dilatation operator acting on your operators, and you want to diagonalize that. And that was mapped into a problem of a Heisenberg chain acting on a state being diagonalized, where the map was that this operator becomes so this is the operator, just becomes a state, which is up, down, and so on. Okay, so the mapping is between the fields. Again, this is the SU2 sector. You can be more general, but let's focus on the SU2 for now. So the X field behaves exactly like an up field, and the down behaves exactly like a down state of a quantum chain. And the Hamiltonian at one loop, so this is the one loop Hamiltonian, is simply up to a constant, the Heisenberg chain. Hamiltonian. Okay. Now, if you're wondering what all this kind of means, like what is this one loop dilatation operator? Maybe I should have said a couple of words, but roughly the idea is that if you have an operator O of X, you can think of it as having some number of fields coming out of it. So this case has 4 scalar fields. And what you're doing is you want to combine it with an O bar of X, which also has 4 fields. So you would do something like this. Normally, that's the correlation function that you're looking for. So this is O bar, well, this is at Y, not at X, O bar Y, O of X. So to do this, you'd calculate these diagrams, but effectively, you can actually cut off this computation here, because these are just normal weak contractions. They're just very simple to do. So you can focus on this part of the operator. And then to add the one loop, find the one loop dilatation operator, then you consider loops that you can have here. So you can think of a loop between these 2 fields, for instance. And then, okay, these ones are 3-level contractions with the other operators, so you can worry about them. You don't need to worry about them. I can just put them there, but these just interact trivially. So when we're talking about the one loop dilatation operator, what you're actually calculating is all the possible loops that you can have between your field lines coming out of your operator at X. So you need to do some one loop computations, and they end up telling you that the problem is, so when I say this, of course, this could be, it could be something like a gauge field being interchanged, or it could be some scalar fields being interchanged. So depending on, so you have to just do the usual loop computations. And if you do all of that, then you find that at one loop, you end up with a very simple quantum mechanical problem. And then this allows you now to go back to my first slides and apply the Bethe ansatz, with, of course, a few complications, which is that you're not only in SU2. In principle, your spin chains live in the whole of SU2,2/4. So you can have excitations with any quantum numbers in this gauge group. So that leads to complications like something called the nested Pythagoreans. But okay, those are not too difficult. You also, in principle, these interactions can change the length of your chain because two fermions can become a scalar or the other way around. So it can actually, there are length changing operations which were not standard, like in the Heisenberg chain. If you consider these bigger sectors. Another problem is that if you want to go to higher loops, and by the way, maybe some confusion sometimes arises here when I draw these diagrams, right? This is, even though it's a finite theory, these are not finite. So these are divergent loops. The extra divergent comes because we are at the same point. So it's a composite operator made up of many fields at the same point, and when you calculate Feynman diagrams, then you do get divergences. So to get anomalous dimension, of course, you need to calculate, properly regularize these integrals and get the right answer. So the theory is finite only in terms of the fundamental fields, not in terms of composite operator. So you need to go to higher loops, and that makes the spin chain more long range. You can kind of see it from this picture, because let's say you have these things coming out. You could have a higher loop. Let's say a two-loop interaction could contain, it could involve 3 lines rather than only 2. So there's a two-loop interaction. So it can become a long-range spin chain, which adds complications as well. And it's not exactly a Heisenberg chain. There's also some extra factors that eventually come up at higher loops. But together with information from ADS-CFT, so from the strong coupling side, which I did not discuss, so this is the geometry. This is the ADS5 times S5, part of the geometry, the master field, if you wish, of this case. And of course, okay, what I forgot really to mention here is that here everything is in the planar limit. So this is the moment where I moved to the planar limit. Otherwise, none of this would really work. You would not be able to write it as a simple spin chain operation. If you ask me, I can explain this better. Then here on the planar limit, so we do have the pure, the classical string theory on ADS5 as also a source of information. So together, all of this information was enough to essentially solve the spectral problem. The solution is not something that you immediately would enjoy looking at, probably. It's phrased in terms of a Y system. Again, this is very related to Hirota type systems. So there's a Y system which is built upon the Dynkin diagram corresponding to PSU 2,2/4. And so you have an infinite number of, well, actually, in principle, you have an infinite number of functions that you have to solve for this Y system, but you can solve them algebraically. So it's something that you can, if you want to know a specific operator, for instance, the simplest one perhaps to look at is the Konishi operator, which is the operator which is trace of phi I. These are just my 6 original scalars. So I goes from 1 to 6. So if you want to know a given operator, you plug it into this Y system, you do some algebraic manipulations. In the end, there will be some integrals that you need to do. But in principle, you can find out the anomalous dimension of Konishi, not at 1 loop, not at 2 loops, but at finite lambda. So you can write delta of lambda, where lambda is now, in principle, can be perturbative, but it can also be very strong. So one of the important results by Gromov, Vieira, and Kazakov around 2010 was to plot the dimension of Konishi. So it starts from 2, of course, because the canonical dimension is 2. And if you plot it with respect to lambda, then it goes, so lambda, it goes here. And I think they plotted up to lambda equals 700 or so. And the plot looks, okay, I mean, the details of the plot are not so important. But what's important is that perturbatively, when you can do perturbation theory, which is kind of here, then it agrees with perturbative computations, where you can do the strong coupling expansion. So you can go to ADS5 times S5, that's when lambda equals infinity. then it agrees with string theory. So this agrees with string theory, it agrees with perturbation theory. In between, you have no way of getting those numbers or those values, but integrability is what tells you. And you get a very nice and precise interpolation for the first time, I think I would say, for a four-dimensional field theory analytically. Of course, you can do a lot with the lattice, and you can get many of these results. Of course, lattice is very difficult for supersymmetric gauge theories, but you can, in principle, imagine doing things like that on the lattice. But this is an analytic computation using techniques from integrability and the Y system to be able to get a non-trivial operator, which is not protected. It depends, its dimension depends on the coupling for all values of the coupling. So that was one of the main achievements of this integrability story. And okay, so to conclude, I think this kind of review of some of these topics, maybe let's say what I will quickly tell you next time. Well, next time, what I'm going to do is kind of try to get to a new frontier in this, because for n equals 4, even the 3-point functions are well understood by now. I mean, things are difficult, so there's a lack of perhaps very explicit results, but in principle, there's no real problems. Now the goal, at least my goal, is to break n equals 4 supersymmetry to n equals 2, also n equals 1. So that's lower supersymmetry, with, of course, the eventual goal of seeing how much of this understanding can go down to QCD, right? N equals 0 with fermions, with quarks, and so we're very far from that. But we, at least this kind of top-down approach, is very far from really saying something about QCD. But these n equals 2 theories, I'm going to argue, give you very interesting features. First of all, you can have multiple gauge groups. So these are theories which can be SUN times SUN, several times, and there can be matter which talks to both of these SUN. And this will lead us to more exotic, we'll use the word dynamical next time, dynamical spin chains. So here you remember for n equals 4, at one loop at least, the spin chain was pure Heisenberg, right? So this is just a purely Heisenberg spin chain, very well understood. Here, the moment you go to n equals 2, you start getting variations of Heisenberg that are not well understood, in particular integrability of these spin chains is not clear. Okay, so of course, integrability is an important feature. It's very powerful, but our goal is to understand, okay, what happens when you try to become more realistic? Because, okay, this is great, but maybe a little bit too special. This is a huge class of theories that we're going to be looking at, which in principle have a lot to offer in terms of insight for more realistic field theory. And if integrability is not a feature of them, then, well, maybe we need to learn to live with that. And one of the ways we're going to learn to live with that is to study the symmetries a little bit more carefully. And it turns out that the symmetries that we're going to end up with are not all of them Lie algebraic. We're going to get something known as a Lie algebroid as part of our symmetry structure of the theory. And we'll spend a little bit of time next time trying to understand what that new structure is, new in this context, of course, and what it implies for the behavior of the theories. Okay, I think that's where I'd like to stop. Thanks, and let's see if there's any questions.
Yeah, so any questions from the audience? Sure.
A bit of an open-ended question, but what do you think we could learn?
A little louder, I don't think you can hear.
Bit of an open-ended question. What do you think we could learn about more realistic theories using these kind of spin chain techniques?
Sorry, could somebody repeat the question because or maybe come closer to the microphone because I could not really hear.
Do you expect to be able to learn for more realistic theories if you continue with this program?
Yeah, what to expect to learn? Okay, so you know, already from here, even for the n=4 case, we did obtain a lot of insight about four-dimensional gauge theory. Okay, it is a non-trivial interacting gauge theory. It has, of course, these properties of conformal invariance as a particular, and that's, we unfortunately have to live with that also with these n=2 theory. So they have less supersymmetry, but they're still conformal. And you can argue that, okay, this is definitely not very realistic, although might remind you that, you know, even QCD or pure Young-Mills, let's say, at one loop is still conformal. The conformality breaks further down in the loop order. So, okay, are we going to learn anything really useful about QCD from this? I mean, I think I kind of doubt it at this point, but, you know, you never know down the line. So here what we're trying to learn is, first of all, a link between gauge theory and what we're going to, maybe I should say, statistical system. So we're starting to see indications of a much bigger duality between, because here it was n=4, had to do with spin chains, and the spin chain language was sufficient. It turns out that for these n=2, it's actually, maybe one has to go to statistic, yeah, I think that it has to go maybe and look further into statistical systems, many of which are not integrable. So our main goal is perhaps to understand, okay, you know, we had many pillars. We had integrability, we had conformal invariance. These are not the same. So let's break at least integrability, or at least go to a situation where integrability is not so obvious as for n=4. Can we still make some progress? Maybe then you can make a bigger link here, also in the non-conformal case, between gauge theory and some maybe more complicated statistical systems that might tell you something about the, you know, the underlying, the spectrum of even a non-conformal theory. So if we can achieve something like that, like some kind of more general mapping, that would, I think, be, you know, significant progress in understanding realistic theory. Also here, we're looking at symmetries that are not Lie algebraic, meaning that we're breaking this SU4 in particular, which was our gauge symmetry, or our R symmetry, the internal symmetry. We're breaking it into some deformed version. You can call it Q for now. Okay, we'll give it a better name next time. But some quantum version of this. Maybe I should put the Q here, actually. And also here, you could say, well, maybe this can be broken in much more, let's say, the more you lower your supersymmetry, but you must still have some remnant, which might give you some kind of, you know, symmetries usually are associated to selection rules. And maybe for some theories, which I don't think are going to be QCD, but maybe much more realistic than the ones we're looking at, you might still be able to learn something by understanding what are the true symmetries of the problem. Okay, I must admit that, okay, of course, I don't think we're going to see, you know, QCD being solved anytime soon in this approach. But I think the more examples you have of non-trivial four-dimensional theories where you can solve, or at least approximately solve, but in some clear way, the spectral problem and the conformal and the correlation functions, I would call that progress.
Thank you. Thanks. Any more questions from the audience? I think we have run, yeah, so we have run 20 minutes over, so I think we can conclude here.
Okay.
Thank you so much for your talk. I really enjoyed it. And looking forward to next week's.
Okay, so next week, yeah, I already kind of told you what roughly